Hello everyone, I am Zach Peterson. Welcome to my channel. Very happy that you're here. Today I'm going to be looking at a viewer question about PCB design for isolated DC-DC converters. Now in isolated DC-DC converters, of course, you have galvanically isolated nets on each side of your transformer, but what about on the input side where you have a VN positive and VN negative? How do you route those, and can you route them on top of each other? That's the essence of this viewer question, so let's go ahead and take a look and get started. Now this question deals with DC-DC converters and how to route the input nets. Let's take a look at that viewer question. Stian Sonderland writes, "Hey Zach, we met once at Azatec's event in Copenhagen. I know you get tons of questions, but I will give it a try. On isolated DC-DC converters, there is always a suggestion with two copper planes next to each other on the top layer for VN plus and VN minus. Would it be better to have, for example, plus on the top layer and the negative net on layer 2, keeping most of the fields contained in the prepreg, or does this not matter much? I would be very happy if you find the time to reply. Best regards, Stian from Norway." Well, I can tell you this, it might matter, but it depends on what's coming in on the VN plus and VN minus nets in your DC-DC converter. Now, you could also take the same approach with the ground nets on each side of the transformer in your DC-DC converter, and so we'll look at some calculations that can justify that. Now, let's take a look at an example in Altium Designer, then we'll get into some calculations, and we'll look at an application note for DC-DC converters, and we'll see what they say about how this affects the field distribution and how it affects EMI. So first, let's take a look at an example project in Altium Designer. Now, those of you who are viewers of the Altium Academy channel will probably recognize this layout. This layout is for the flyback converter module project, and you can take a look at the video for that project in the description. Here on the top side, we have our 120 volts AC input net, and then here on the bottom, we have our neutral line. And then here in the center, we have an earth connection, which is being used to take advantage of a differential and common mode filter made up with these capacitors. So here on this input line, you can see that I have it on the bottom layer. I could just as well put it on the top layer, and everything we're going to talk about here is going to be equivalent. Now here in this example, we do have some capacitance between this line and earth, and then between this line and earth. And if we were to just totally eliminate the earth line and we were to route these two input lines, so the line voltage and then the neutral line, together on the same layer, there would also be some capacitance between them. And we can actually calculate what that capacitance is, and we'll do that here in just a moment. Now, what if we were to instead put the two traces right on top of each other? How would that change things? Well, you would have some electric field confinement between the two traces. Now, you still have an oscillating electric field because this is an AC input, and if it's an AC input, that means you're then going to also generate a magnetic field. So there is still going to be some noise at 60 hertz or 50 hertz, whatever your line voltage frequency is. But because we put the two traces on top of each other, or if we route these as polygons and we put those polygons on top of each other, we would expect the field to be better confined between those two pieces of copper. So we can compare those two situations just by calculating the capacitance for similarly sized rails based on whether they're on top of each other or whether they're in the same layer right next to each other. Now, this project is dealing with an AC input voltage, but what if we were dealing with a DC-DC converter? How would things change? Well, if we have a DC-DC converter, of course, we're bringing in a DC voltage, but that DC line could have some noise on it. Where could that noise come from? Well, you could have an upstream switching converter, which then has some switching noise present on that input DC-DC line. You could also have common mode currents coming in on those two pieces of copper, which would then create strong radiated emissions around the PCB. Now, that's one of the reasons that we put this capacitive filter in the flyback module, because it helps to deal with those common mode currents and then sync them back into that earth connection. Whether you have an AC input or a DC input with some switching noise, it doesn't really matter. There's going to be an oscillating voltage between those two pieces of copper, and that's going to create some radiated emissions. So putting the two pieces of copper on top of each other might be one strategy to help contain the field inside the PCB. Now, there's actually something very related to this point which you didn't ask about, but which I will bring up, which is the fact that there could also be a similar oscillation between the grounds on both sides of the transformer. Let's take a look at that flyback module again. Now, if you look over here in the center of the board, you can see that we have our transformer, and then we have our two ground nets on each side of the transformer. Here we have our primary ground, and here we have our secondary ground, which I've just labeled GND. Now, these are physically disconnected pieces of copper except for this capacitor. Now, the purpose of this capacitor is it is a Y-type capacitor, or a class Y safety capacitor, and its entire purpose is to allow high-frequency currents on the secondary side to flow back to the primary side. That way they can dissipate at the power input rather than created radiated emissions from the secondary side of the board. But let's just suppose for a moment that instead of having these two pieces of copper on the top layer right next to each other, what if we also put them on different layers and we had them overlap, similar to the situation you're describing with the VN plus and VN minus nets on the primary side of this DC-DC converter? Would we expect a similar effect due to the capacitance between them? Let's take a look at some calculations to see if we actually get appreciable capacitance in these situations, and then we'll take a look at an application note that shows some radiated emissions measurements. Now, to do these calculations, we don't need an electromagnetic field solver, although you can use an electromagnetic field solver. We can actually just use some closed form formulas that you'll find online. So here I'm on emisoftware.com, and you can see that they offer several calculators for calculating capacitance between different geometries. Now here we're looking at the coplanar capacitance model, where we basically have two pieces of copper in the same plane with the same geometry. Let's take a look here at the values we can put into this calculator and some typical capacitance values that we could see. So here, let's just assume that we have two pieces of copper. They're on the top layer of the PCB. And here I have a 1x2 piece of copper, 1 inch by 2 inch piece of copper, I should say, separated by 1 millimeter or 40 mils. Now here you can see with a relative permittivity between these two pieces of copper of 3, we get about 4.5 picofarads of capacitance. Now, why did I use a value of 3 for the relative permittivity? Well, that's because this is approximately going to be the effective permittivity that you would expect for microstrip traces. And so we might expect a similar value for the relative permittivity in this case of coplanar pieces of copper. The reason we need to use an effective permittivity is because on the top side of the copper we have air, while on the bottom side of the copper we have our PCB dielectric with a decay value of anywhere from 4 to 4.8. So in this case, I'm taking an estimated value of 3 because that's an effective decay value we might expect for microstrip routing. Now, even if I did use a decay value of, let's say, 4.5, just as example, you can see here that we still only get about 6.8 picofarads of capacitance. Now let's go ahead and compare this to the biplanar capacitance, where we basically have two pieces of copper on top of each other, but on different layers. Now here, we're going to separate them by that same 4.5 relative permittivity. We're going to use a 1x2 piece of copper, so 1 inch by 2 inch. And then we're going to have a separation that would correspond to the typical value we might see for a 4-layer or a 2-layer PCB. So for a 2-layer PCB, this would probably be about 60 mils. And you can see that with a 2-layer PCB with the two pieces of copper right on top of each other, we get 33 picofarads of capacitance. So significantly higher capacitance than in the case of coplanar pieces of copper. What if this were a 4-layer PCB and we had these two pieces of copper on our top layer and on layer 2? Well, in that case, we might have a separation between them of as low as, let's say, 10 mils. Now with 10 mils of separation, we get 200 picofarads of capacitance, significantly higher capacitance. That corresponds to much stronger confinement of the electric field between those two pieces of copper. So initially, it does appear that we can get much stronger confinement of the electric field just based off of these capacitance calculations between our pieces of copper. Now let's take a look at an application note that looks a little more deeply at the radiated emissions from an isolated DC-DC converter based on these different arrangements of planes. Here I have an application note from NVE Corporation, and they are looking at radiated emissions from NVE's isolated DC-DC converters in the case of a 4-layer PCB. Now here you can see they've identified some of the common problems that lead to radiated emissions from an isolated DC-DC converter. And you can see here that they have capacitor placement as one of the big ones. That one should be obvious. You also have the potential for edge emissions. But one thing here that you can see in this lower part of the layout example is input to output dipole emissions. And this is essentially the type of emissions I was referring to when we looked at the flyback converter example. And one of the ways you would take care of this is by putting a capacitor across the two sides of this module. Now, one solution that they propose is to do something like this, where you have the internal ground on the output side overlapping with the internal ground on the input side. Now, this is where you would create some capacitance between the two ground nets rather than placing a discrete capacitor to connect them directly. And you can see that this is modeled right here on page 3. If I just scroll down here to page 3, you can see how they've modeled the capacitance that gets created between these overlapping planes. Now, of course, the overlapping planes on the output side can't get too close to the other plane on the input side. You do have possible arcing paths, but overall you do create some overlap area. And the overlap area, as well as the distance between the two planes on each side of the converter, creates that capacitance between these two rails. So how does this affect radiated emissions from this PCB layout? Well, if we take a look at the last 2 pages of this application note, you can see that they do provide some example radiated emissions measurements from their evaluation board where they have implemented this style of overlapping planes in their DC-DC converter. Here you can see at the low frequency range that we do have compliance with radiated emissions limits, and you can see that they stretch this all the way out to 6 gigahertz. And again, at both power levels, you can see that we have compliance with radiated emissions limits just using this overlap between the two planes to provide capacitance. So I think all of these results, the basic calculations, as well as the placement of ground in the PCB layout, justify the use of overlapping planes to provide capacitance, which then provides that return path to the primary side for high frequency currents from the secondary side of your DC-DC converter. Same concept applies to your VN plus and VN minus rails. There could be some switching noise that exists between them, or it could be an AC signal, and if you put those two rails on top of each other, you're going to confine the electric field in that dielectric region between the rails. Now remember, this isn't an even-or situation. Even if you put the two pieces of copper on top of each other to confine the electric field between them, you can still place a capacitor across those two rails or across the two ground planes. Placing that safety capacitor is advised anyways because it's going to provide the control that you need over EMI while still maintaining galvanic isolation. Thanks for watching this video, everybody, and let me know what you think of this type of layout in the comments. Make sure to hit the like button, hit the subscribe button. As always, if you send me a good question, it might end up in one of these videos. I'll see you next time, everybody.